Go ahead, group one.
In the next few minutes, we will mention the background, methodology, experimental results, and future directions of our study.
Okay.
And the goal of this study is to utilize deep DNN to reconstruct barycentric interpolation functions. Our main text includes the text one is to construct a single interpolation function, and the text two is to generalize across multiple interpolation functions. To evaluate model performance, we use MSE as the primary metric and train our network using the ADAM optimizer.
Okay.
In the background, barycentric interpolation is an efficient interpolation technique that calculates ways to obtain a smooth interpolation curve. However, traditional interpolation methods face several challenges. Noise, like noise sensitivity, nonlinear distortions, incomplete sampling, and DNN offer a solution by leveraging their nonlinear mapping capabilities, which improve generalization and accuracy in function approximation. Next, we will have another team member introduce the details of the task.
Hi. So I'm gonna talk about the task one. Okay. So in this task, we are focused on single input to single output. So to reconstruct the original function. So here's some basic steps for we to finish the task one. So the most important part is we set different parameters. So for example, so in the original setting, we have 25 sampling points and 512 total points. And for the DNN parts, we have 3 layers and 64 neurons in each layer, and we're using ReLU function. So here's our observation result. So if we change the sampling point big M, so we can see that when the M is increased, so the DNN, the currency of DNN is better. So if the sampling point is too less, so it will not have an accurate function to generate.
So which activation function you use here?
With sin 2 pi x. Yeah.
Come
It's
again?
a sine function.
No, the activation function for the DNN.
We do.
Which one?
Sure. This
ReLU.
function. Value. Okay, yeah. Value function. And we use 3 layers and 64 neurons in each layer. So that's the initial setting. Yep. And we increase
Can you go in presentation mode? Yeah.
Okay.
Good.
So if we keep increasing the sampling point, we will see some unstable phenomenon happens in the interpolation, because in the background we have talked about, so because there's a factor of 1 divided by xi minus xj, so if the sampling point is too close, so it makes the omega I to be very large, so it turns out that is unstable. Yeah, but
because can you go back to that function that you just showed?
Sure.
Yeah. So have you studied poles and zeros of a function?
Yeah.
Yeah. So you see that you have a bunch of poles, right?
Yeah.
So whenever at the bottom, right, you have a polynomial,
Yeah.
And whenever the polynomial is a 0, right, you're going to have a pole, and the pole is going to give you that jump. And so the question is, what is the location of the poles, right? Because you are interpolating the interval 0, 1. What's an interpolation interval? 0, 1, right?
Yeah.
So the question is whether the poles are between 0 and 1. And the more interpolation point you have, the more the poles are going to end up in 0, 1. And so you have a spike to infinity. Go ahead.
Okay. So yeah, so the barycentric interpolation will be unstable. So in the result. So but when we look at the DNN prediction, we can see that the model can do better. So since we have more training data into the model. Okay. And next we observe the layers in the DNN model. So we tried different number of layers when we are training the model. So when the layers, and we only have one layer, so the results are not good. So we keep increasing the layer. And we found that it will have some overfitting in this case, since we don't have too much feature to analyze in this task. So when we make the layers to equals to 20 layers, so the results are not good.
Okay, can you go back a second? Let me just see a little bit. Go back one slide. Okay, so L1, yeah, you see L1, you have a ReLU, right? So basically, you see that the function is just a linear function.
Yeah.
Then it becomes, yeah, okay, good. How many iterations did you do for this network?
Iteration.
Yeah, in the training.
You mean the approach when we are training?
Yeah, epoch. Yeah. How many epochs?
2000 is suggested in ChatGPT.
Of course. Yeah, because you want the network. So basically, so you see when L equal to 1, your loss is not going to go to 0 because you cannot, with the activation function that you have, you cannot match all the points, right? But then you see that after you do 2 and 3, then you count on the fact that the network will become overfitting, right? So that you force the network to exactly pass through the points, right? But you see that when you go to L equal to 20, then you no longer pass through the first 2 points, right?
Yeah.
So you see that you lose the ability to interpolate the points when you have too many layers.
Yeah.
Okay, go ahead.
So next we observe the change between the neurons in each layer. So we try
How many layers here?
3 layers.
3 layers, okay.
The initial setting is
Okay,
this.
right. Good.
Yep.
Good.
So we just change the single parameter in each type.
Understood.
So we start from 16 to just increase the neurons. So we can see that when the neurons is not enough, so the curve formed by the DNN cannot fit the sampling point, and it's not good. So yeah, it's not good. So we keep increasing the neurons in each layer. So in this case, we found out that there's no big difference in this model. Maybe
the difference is the complexity, right? So if you have to implement the network, having 10 new or 16 neurons or 2000 you will pay in complexity, you will pay in energy, you will pay in cost, right? You will pay in time. So
but not big improve to the result.
Yeah, so the performance doesn't change, but you're wasting resources basically, right?
Yeah.
Good.
Okay, next. And also we try some different method to set up the neurons in layer. For example, we use 5 layers here. So from 6, if we increase the neurons in each layer every time, just from 16 to 256. So and also we try the decrease way, and also there's no big improve. So we think it's not a good strategy in this task.
It's a simple task, right?
Yeah, it's a simple task. So there's not big improve on it. Okay, next is we try different function, so we can know the power of the DNN. So we have some polynomial function here, so it's good. So it's same as the barycentric interpolation. And also we have tried some slightly complicated function here. We try a sinc function here, so we can see that both the barycentric interpolation and the DNN is not good enough. So we need to change so we try to deal with this problem. Yeah, but first we want to observe the function of the activation function.
Yep.
Yeah. So so initial setting is the value function. So it looks like this. So and next we all use the linear activation function in the end. So it basically is a linear approximation model. Yeah.
Good.
And next we try sigmoid and the Swiss function. Yeah, and we can observe that the sigmoid function generate a smooth layer, but it's not fit in the sinc function because the sinc
Sorry.
function oscillate very fast.
Question.
And
So this is question. So this is 3 layers. How many neurons per layer?
64.
64 for all 3 layers, right?
Yeah, all 3 layers.
And 2000 interpolation. You cannot match the sigmoid. Interesting.
Yeah.
Interesting.
And
Yeah, go ahead.
and the switch function, so it's slightly better than other function in this case. So it works better in this case. But after I changing different parameters, so that's one of the way that I tried to let the DNN prediction to fit the original function. So I chose the big M equals to 100, the sampling point to 100, and I use the Willow function and 128 neurons. Yeah. So and the most important factor is the sampling point. So if you put more sampling point to the DNN, so the DNN can learn better. And the second important factor is the activation function. So I use Willow function here, but so yeah. But I didn't try the combination of different activation function. So because it takes lots of time. Yeah. And also I slightly increased the number of neurons because it can put on more information in each layer. Yeah. So for the conclusion in this task, so for the data scale effects, if we use too less training data, so it will have the problem of underfitting. And the width of the network can store the information, store more information. Yeah, and the depth of the network can analyzing the feature, and it cannot be too much. So otherwise, it will have some overfitting problem. And for the activation function part, the Willow function and the switch function is powerful in this task. So now the other teammates will talk about task 2.
You are muted, eh?
Hello. Okay, here we start the task 2. 怎样变成 presentation 啊？
Yeah, you can go presentation mode. Yeah, that one.
Okay. Here is task 2. The task 2 is function family generation. here is 100 dimension input to 512 dimension input output. Okay, first we set the random seed for reproduction and generate.
Reproducibility. Okay. Reproduction is when you have kids. So let's say reproducibility.
Generate random function now used by semantic interpolation to construct the function and create the data set. Then we use the DNN model with ruler and train the model, evaluate order on the text, and then this is the generate function. I use 3 sine wave to the function is formed by the superposition of 3 different sine waves. A is amplitude of sine wave. F is the frequency of sine wave. Phase is phase. Then this is the function in Max formula.
Okay.
Then we this with a sample point. We take 100 sample points. This blue line is true function, and red dot is the sampling point.
Okay.
Then this is the barycentric interpolation and and with the sample point.
Okay.
Then this is the DNN prediction and the sample point. The layer is 3 layers and the neural is 250.
Okay.
Okay, this is DNN prediction vs the barycentric interpolate function. Interpolate function. This is the true function vs DNN prediction function. This also 3 layer and neural is 250. This is also the blue line is true function and the black line is DNN function. This is 1 layer and the neural is same as 250.
Can you go back to the go back? Can you go back? Go back. Yeah. So by here you generate a data set of functions, right? You just don't generate one function. What's the size of the data set?
512.
No, that's the size of the X and Y, right?
Yeah.
I want to know how many random functions do you generate?
1,000.
Okay, go ahead.
Then the experimental result generation capability never successfully generate global function from limited data. Never achieve deeper vs y. With the never better capture high dimension relation parameter turning 这个 significant impact from change in sample number.
Correct.
Conclusion and further improve. Barycentric interpolation is simple but can fully generate the original function. DNN can simulate the function if you have a lot of training data and good setup. The future improvement can try combination of activation function in DNN mode. Okay.
Very good.
Okay.
Very good.
Thank you.
So just one thing. Can you go down at the function generation? Can you go down at the function generation? Go down, go down. Go down. This. So here, try to generate the function as follows. You randomly generate the coefficients of the barycentric interpolation, and then 听得到吗？
听到。
So here, so here, instead of generating a cosine function, try to generate the coefficients of the barycentric interpolation, right? Because the family of function that you chose is too simple, right? Because you see that you just have the function is very simple. So instead, what you can do is that you can generate random. You fix a degree of the barycentric interpolation, and you generate the parameters of the barycentric interpolation. So you have a wider set of functions. You see that here you have 6 parameters, right? You have 6 parameters. So it's too little, right? Try to generate, let's say, a degree, because that's something that you can do. You can make the function more complicated by choosing a higher degree of the barycentric interpolation formula. And then you see how the function loses power to represent the function as the family of function becomes larger. You see, this is 6 parameters, right? And you have a network of 3,000. You have how many neurons in total? Like 128 times 3, right? So you have 750 neurons to learn 6 parameters. So it's an easy job. It's an easy job. So if you instead you generate random coefficients for the barycentric interpolation, and then you build the family of function as a family of random rational functions, it will be more interesting. Okay, Ma? Okay. So for the final submission on Friday, try to do the same experiment, but just change this function. Okay. Can you show me as the degree of the interpolation grows, how harder the job is? Okay, Ma?
Okay.
Okay, go ahead. Group 2. Any questions for group 1 while group 2 will get ready?
I want to ask a question. So in the E3 submission on Friday, so is it a must to make a video record? Because it spends a lot of time.
To do the video recording, you need a lot of time?
Maybe, yeah.
You just turn on the webcam and you record yourself, right?
Okay.
Trust me.
So,
This is the most useful thing, is to hear yourself talk.
okay.
Especially when you are speaking in a foreign language, and when you're trying to speak clearly and concisely, like looking back at yourself talking, it's so difficult. It is so difficult.
Okay. Thank you.
Any other question for group 1? Otherwise, we move to group 2. You use the simplified Chinese translation. Come on. Use at least the English translation, right? Not the simplified Chinese. God damn it. Okay, if there is no group, no question for group 1, let's go to group 2. I hope I don't forget about group 5 this week as well, like last week. Okay, group 2, go ahead.
Yes, can you hear me?
Yes.
Okay. Can you see the PPT?
Yeah.
Okay,
Very
okay.
nice. So you use Canva, very nice.
Wait a minute. Oh.
Tamala. Go ahead.
Okay. This is our presentation, and we are group 2.
I think you have to change something.
Do you see the?
Yeah, try to go in presentation mode. Go in presentation mode.
Oh.
I think.
Do you see the?
I think you have to change you have to share the window. Go back and share the window with the presentation, not the web page.
Oh, let me solve this problem. Wait a minute.
Because when you go in presentation mode, we don't see the presentation. That's it. Finger crossed.
Okay.
Okay.
Is this right now?
Yeah.
Oh, okay. Thank you. And we are group 2, and now we are going to our presentation, our Python challenge 1. At first, we wanna introduce the something mathematical formula in this project, and this is barycentric interpolation, and this is the very high efficiency and some numerological stable method for the polynomial interpolation. So in this project we need to use this formula to do our DNN predict. And this formula is simply based on the traditional interpolation. The formula name is Lagrange interpolation. So why we don't use the traditional interpolation? As you can see in this formula, we need to do a lot of time, a large number of time of multiplications calculation. It is very waste a lot of time when we having a lot of sample point, sample number. So for solving the problem, we can use the barycentric way to pre-compute it to avoid the redundant calculations, and it can make the position calculation position to more faster.
Let me ask you a question. Very important question.
Okay.
Lagrange, where is Lagrange from? Lagrange is a mathematician, right? What's the nationality of Lagrange? What's the nationality? What's the nationality of Lagrange?
German.
You failed the class. Failed the class. Try again. Somebody can help him?
Same as our professor here.
Correct, right? Correct. It's Italian. Go ahead.
Oh, okay.
Don't forget, Don't forget.
Okay.
Go ahead.
And this is the simple DNN model structure, and this also we use in this Python challenge, and you can see the yellow point is the input layer, and the green is the hidden layer, and the last is the output layer. So the input layer we will receive the data, and the hidden layer we wanted to learn the interpolation function through the weight sum and the activation function, and the output we will predict the new interpolated value. So it is the one point of the hidden layer, and we will call it is neuron. And this part is DNN. One part is called forward progression, and we will complicate the weight sum and apply the activation function. And this is the formula. This is the formula. And W is the weight, and B is the bias. Bias is we chooses the we choose how large is this, and the X is the input value. The always will uses by the matrix form, And what is the activation function? What is the activation function? And this make the neural network is not the linear. If this can help the model can learn the complex pattern. If we don't have any activation function, and the network would only perform the linear task. So the next step is to calculate the loss. And in this project, we will use the MSE, the mean square error. So n is the sample point, and the yi is the real value, and the yi is the predicted value. So it means the smaller MSE is usually means the error between the model predicted value and the true predicted value is low. It means it indicates a better fit. The model is good enough. The last part of the DNN is the back propagations, and it computes the gradients for each layer using the chain rule, and it can update the weights accordingly. So the formula of this is the traditional gradient descent, and it have another name is called SDG, and this one is the
SGD. SGD.
SGD as
Stochastic gradient descent.
and this one is the learning rate, and the L is the loss function, and we will do the calculate the gradient of L. But in this project, we will use the ADAM optimizer to update our weight, and it improves the port set by updating learning rate for the model can faster convergence, and this is the ADAM function. And the next part is our result presentation, and I will and we will have another teammate to introduce it.
Hi. Could anyone see my slides?
Yeah.
Okay, please wait a second. Okay, so here I will introduce what we have done on task 1.
Sorry, aren't you group 2? You're group 2, right?
Yeah, we are.
Oh, we're group 2, and the part
because
that
the first slide said group 1, right? So I was confused. It's like, are you the right? Yeah. You understand what I mean, right? Go back one slide.
I'm wrong. Group 2.
You're group
sorry,
2, right?
Yeah,
sorry.
right wrong. 你再重新跟进去一次，重整一下，应该会改。
Okay, I have seen the update. Yeah. Okay.
改。
Go ahead. Because you used to be group 1, right?
Okay,
Go
so
ahead.
next I'm going to introduce what we have done for task 1. First of all, we have built an original model. It is trained on 20 data points and has 16 hidden dimensions, 1 hidden layer, and uses ReLU as the activation function.
How many iterations? How many epochs?
2000 epochs.
ChatGPT
Yeah.
says 2,000 epochs. Okay, go ahead.
Okay, and we increase the number of hidden layer to 2 and 4 respectively. We can see that the test loss values of these two cases are lower than the original one. However, the test loss value here is a little bit higher than the two hidden layer model, and we conclude that this phenomenon is due to an overfitting issue. While increasing the number of hidden layers can increase the ability of the model to learn new features, it might also increase the complexity of the model as well. So the model tends to feed on features from noises. So this is the case of increasing the model states. For the next case, we increase the model's width. And based on the same logic, we want to increase the parameters of the model to enable or to enhance the learning on unknown new features. And we can see we increase the number of hidden dimensions from 16 to 20 and then to 32. We can see that the test loss values drop along the way, and the model can regenerate the unknown function more fluently. So this is a case of increasing the model's width. Then we increase the number of data points from 20 to 100 and then to 200. For the case of 100, we can see the test loss value is lower than the original one. However, the value gets higher in the case of 200. We conclude that this is due to the issue of uniformly distribution of data, because the newly generated data we use is picked randomly from the interval of interpolation. And this randomly data, some of them might be too close to the upper limit and some might be too close to the lower limit.
But it's also because the interpolation goes crazy, right? You see how many peaks the interpolation has, right? So the interpolation becomes less predictable, right? So before you were interpolating a nice smooth function, right? And now your ground truth is so jumpy. That's the reason, right? It's not. I don't think it's data distribution. It's the fact that the function becomes crazier, right? You see how many peaks you have, right?
I see. So the number of peaks increase. Yeah.
So that's a issue. It's not the data distribution. Go ahead.
Okay. Thanks. Okay. So finally, we have changed the type of activation functions. We use ReLU and sigmoid during our training process. And we can see that for the case of sigmoid, the value of test loss is much higher than the other two cases.
Do you have a? Do you know why? Do you have a suspicion? Do you know why?
We have discussed this phenomenon and conclude that this might due to a gradient vanishing issue.
Maybe. But another issue is this: what is the range of output of sigmoid?
0 to 1.
Correct, right? So what happens here in my mind, it's the fact that you cannot match this -1. Because if you look at the sigmoid, right? Of course, these are multiple layers, right? But the sigmoid saturates, right? So basically, you don't have. What's the depth? What's the depth of this function? This is how many layers? 16 hidden dimension, right? You have only one hidden layer, right?
Yes.
So you see that your function is able to catch the +1, but then he has to transition to the -1, and yeah, basically the output they don't have enough dynamic range to catch both the +1 and the -1. In my mind.
Oh, I see. So
Yeah, because you have to transition between -1 and +1, and this transition is very long, right? It takes a large set of amplitudes of the weight to transition between -1 and +1, and your network cannot catch up with the variability of the function, in my mind.
so should I add more layers to fix this issue?
So, yeah, so if you add more layers, it should be easier. Yeah, it should be easier.
Okay, thank you.
Go ahead.
And this is the end of our introduction for test 1.
Okay.
Now the other teammate will explain test 2.
Okay.
Okay, so before I introduce the task 2, I want to show the code first. I want to introduce, because that task 2 is actually just more samples of task 1, that it does more complete things again, but it takes more data. So let me show the code first. That the first part is that we randomly sample endpoints.
Very good. Very good.
This part we randomly sample endpoints and then generate corresponding y value, which will return.
So you have just a second. So the x, what's the x range and what's the y range? So the y range is -1.
It's actually just build a barycentric interpolaar builds on these points.
No, I understand. I'm just asking you what is the range of x and y, right? Because the y is between -1 and +1, and the range of x is 0, 1. Okay, good. Go ahead.
Okay.
I just wanted to see what is the yeah.
It's just a build of the barycentric function.
I understand.
And then next part is this one. Is get sample index. Is to choose index from 4 grid X and based on the select sample methods, which we have uniform, random, or irregular.
Excellent. Very good.
And next part is data preparation. In this part.
Just a second. So how is it irregular? So you have 2 clusters in the irregular one, right? So
yes.
what do you do in the irregular? Go ahead.
Irregular is that it forces an irregular pattern by selecting points from 2 clusters. Like it has three kind of methods. Like uniform is like equally spaced index over 4 groups, and random is like just randomly select n samples index without replacement, and then try to sort them. And irregular is that force an irregular pattern by selecting points from 2 clusters.
Yeah, so the first cluster is between 0 and half, then is like half and there, and you have, wait a second, but look at the second clusters. So half of the point, just a second. So how are the 2 clusters different? Tell me. Because the first cluster is between 0 and x divided by 2, and you take half of the samples. And the other one is still between 1/2 and 1, and you still take half of the samples. I think you should change it, right? I think you should change it like, for example, the first one is n sample divided by 2, and the other one is the n samples divided by 3, and the other one is n minus n sample divided by 3.
Oh, okay.
You understand what I mean? Because you see that I suspect that the uniform...
1 divided by 2, it's just like probably divided by 3, like that.
Yeah, exactly. So that you have more points in one interval and less points in the other one. That's my suspicion. That's my
All right.
suspicion.
I understand it. So probably I can change this part.
Yeah,
And
go ahead.
next one here is to generate data set, generate M functions based on the barycentric interpolations.
Good.
Yes, basically just like that. And then next part is to build a DNN model, which build a simple feed-front network, neutral network, which mapping a 100-point input to 512-point output. And then it started to go to the training and evaluation parts. Here it's just doing training and evaluation and try to plot it out. And then I'll go back to my my parts, my PDT parts. PowerPoint here. Okay, here comes my PowerPoint, and it's just what it said. X-train is 100 sample points for each function, and Y-train is predict 512 sample points. And dataset is 1,000 function, 80% on training and 20% on value, and it's the model structure. And loss is MSE. And the hyperparameters epoch is 100 and batch
Only.
Batch size
Yeah.
is 32, and early stopping is 10 epoch without improvements. And here's comes out results. This result is come of using ReLU that you can see that it's not really matches the prediction is not really match the true function in some parts. In the smooth parts, it can just simply predict it, but if it has some
Wait a second. So this is your f of x, right? This is your f of x.
right.
And your f of x goes all the way to minus 60,000. But you sample points only between minus 1 and plus 1 and 0 and 1, right?
Right.
And this is the uniform sampling? No, this must be the random, right? This is the random uniform sampling?
Yes, random uniform sampling. And these three are just randomly taken out from
Yeah. Can you go to the next one? Go to the next slide. Go to slide 10.
Yeah, slide 10 is using ReLU.
I try to check your code. There is something weird, right? Listen to me. So the sample points that you take are between 0 and 1 with x and 0 and 1 in y, correct?
Right.
And you build your barycentric interpolation, and then you resample 512 points for this. It is very strange that you go between such large values, right? Because the points that you sample are minus 1 plus 1. How the heck do you go to minus 60,000? Right?
It goes to 60,000.
You see, you have minus 40,000, minus 60,000. It means that the interpolation is so unstable that you jump down of so much. It's kind of strange, right? Do you see my point?
Yes, I kind of understand. That is that
I mean, you don't have to tell me now, but I just want to point out that it's kind of strange, right? Because the function should be in the box minus 1 plus 1 minus 0 1 0 minus 1 1, right? That it should be in this box, and it's strange that it jumps down so much. And in both cases, it jumps down at the end of the function. So yeah, something strange.
Okay. Let me think of anything.
No, you don't have to answer now, right? But go back and check because there is something strange. Because then, can you go back to the presentation?
Okay, presentation.
The issue is that then you are asking a DNN to have this very large dynamic range, and you only have 3 layers, so it's it's hard for the network to catch up.
here.
Yeah. Yeah, try to check. There is something fishy, but don't worry. Go ahead.
Okay. So here's two results of using. One result is using ReLU, and another result is using JReLU. Yeah, that's using two different functions. And so I want to ensure about the where part. Is it that the output isn't really matches the?
Yeah. So you're sampling points between -1 and +1 on x. Sorry, between 0 and 1 on x, and -1 and +1 in y, correct?
Right.
Then you build a barycentric interpolation on that, which is a polynomial interpolation, correct?
Correct.
So then the polynomial interpolation is gonna, I mean, it could, it could have some peaks and so on and so forth. But basically you see that when you, so the polynomial interpolation is gonna go to -infinity and +infinity at some point because it's a polynomial. And so the behavior that you have should occur outside the interval 0, 1, right? Because you are sampling the point 0, 1. So it's understandable the polynomial interpolation will go to plus and minus infinity, but it should be further away from the 0, 1 interval. I do not know why you have these very strong values so close to +1 and -1. You understand?
Oh, because this this is randomly choose few samples from the validation sets to assess the reconstruction quality. It's not.
Of course. But you see that your sampling points, they go up to 3,500.
Right.
So it's kind of strange. So the polynomial, you have 100 points.
Oh.
Yeah, so because basically the sampling points that you have, they should be still close to like -1 and +1 in the interval 0, 1, basically. It's just my intuition.
All right.
Yeah, just try to check because you see also the presentation before. No. Anyway, so everything is okay. So everything is good. Just check that this high range of high dynamic range makes sense. If this makes sense, it's because I'll tell you now. Your interpolation points, they are all around 0.5. So force the first and the last point in the interpolation to be in 0 and 1. Okay.
Right.
So if you do that, then the function must be in the box in the interval 0, 1. Okay?
Okay.
Go back to your function. Go back to your sampling function. Go back to your sampling function.
You mean the code part?
Yeah, go back to the code. Yeah. Yeah, so here to the points, go up to the points. Go up to the points. Go up one more. Yeah. So to the samples always add, right, in the get sample index. Yeah, in the generated barycentric function, always add an x sample in 0 and an x sample in 1. Okay.
Always x sampling 0 and x sampling.
So the function, right, is always passing between some points in 0 and some point in 1 that are between -1 and +1.
Between -1 and +1.
So on the x-axis, you force the points to have a 0 and a 1. Okay.
Right.
For this value in 0 and a 1, you pick a y-axis which is between -1 and +1 and -1 and +1, so that you're sure that the function doesn't shoot up to infinity.
Oh, okay. So I have to change my x sample parts.
Because my suspicion is this: when you generate the points, they are all around 0.5. Right. And so when you build the polynomial interpolation, it goes to +infinity or -infinity around 0 and 1. And so now your job is very difficult because
Yes.
because the range of the polynomial function is so
Oh,
large.
so I have to ensure that my examples is not around at 0.5. It's like probably
Yeah, something like that. Yes.
Yeah.
Because my suspicion is that something is happening. And also, also when you show the figures, also show for the different sampling indexes, right? The uniform, the random, and the irregular. Okay.
Okay.
So add some figures about that. Do you have some figures about it now or not?
What?
So you in the get sampling indexes, you have 3 different methods of generating the samples.
Right.
In the presentation, do you have different results for different methods, uniform, random, and irregular?
No, I think.
Okay. Just put them in the final presentation, please.
Okay.
Okay. Good. Go ahead.
And then oh, okay, and then that's probably the end of our presentations, and probably I could add the
different methods.
The different methods parts. Yes, that choosing uniform, random, and irregular. I'll probably add it at the end. Yeah.
Very good. Very good.
Because
okay. Any questions for?
Because in the code I can change it just quickly by just changing it uniform, random, or irregular.
Yeah. It's not a big deal. Okay. Are there some questions for group 2, guys? Okay. If you have no questions, let's take a 8 minutes break. I'll see you back at 9:30. Go walk around, drink some water, and go to the toilet. Okay. Ciao, guys. See you back in 8 minutes. Group 3, we are ready for you. Group D, we are ready for you.
Okay, group 3. So so I'm responsible for task 1. And our original function is the same as the document. And our network is 128 by 128, a network with ReLU activation. And it takes about 70 epochs to converge.
Mm-hmm.
And this is our variation. We change the neurons to 10,000 and equally distributed to 1, 2, 5, 8, and 10 layers. And this one is activation function with ReLU. The two-layer model never converged. We speculate it's because the gradient descent process for 2 layers with 5,000 neurons is too coarse compared to more layers, and it has a higher proportion of dead neurons than one-layer model. And the one-layer model with a lot of neurons is basically act as a universal function approximator. So
Question: what is the dead neuron?
Like when the output of the previous neuron is less than 0, then okay.
Go ahead.
So it didn't output anything. Yeah.
Did you verify this somehow? Did you verify?
I'm sorry. Can you say again?
Did you verify this?
No, but we done research. So
I mean, you can verify, right? You can verify because you can, when you do inference, you can just look at the intermediate value and see if this is true or not, right?
Oh, okay. So
I mean, I think you should do it. I think it'll be interesting too.
Okay.
I think it's interesting.
We will do it.
For the final presentation. Go ahead.
Okay. And changing the activation function to sigmoid, the predictions are better, but no. Okay, the predictions are very bad. They all give a straight line prediction, and we speculate that this is due to the severe vanishing gradient problem of sigmoid function, and the nonlinear region of sigmoid is rarely utilized. So all the layers are just linear combinations.
So you had this is why is the 10 layers always flat? There's something wrong here. Huh? There's something wrong. There's something wrong. Yeah, because then there is something wrong. Huh? So you have a bias. Do you have the
by-
code? Do you have the code?
Yes.
It shows the code.
Set.
Now look at the loss. The loss is 1, right?
Losses. This is not the sigmoid one. This is, I think this is leaky ReLU, or so we don't have the.
You don't have the sigmoid.
We don't
Yeah,
have
it's
the
very
sig.
strange. Very strange. You have a bias, right? You have a bias, right? In the
Yes.
sigmoid, do you have a bias?
Yes.
No, it's something weird. It shouldn't be that way. Go ahead. Because you saw the other group, right? So they could still interpolate the function, right? And especially with 10 layers. It's very weird.
The interpolation is still okay, but it's the models that has learned badly.
Yeah. So, but the model is also interpolating, right? The model is also interpolating the points. Correct?
Oh, okay.
Go ahead.
Okay. So after changing the activation function to ton, only 1 layer and 2 layer model give straight line prediction. And we think this improvement over sigmoid is due to ton having a less severe vanishing gradient problem, and making deeper models less likely to enter the linear region of ton. And finally, leaky ReLU produce the best result. It avoids the vanishing gradient and dead neuron problem by allowing this small non-zero gradient for negative inputs. So all neurons can learn regardless of the region of activation function they're in.
Good.
And we have also tested with 1,000 neurons, and only the performance of one is about the same. It's about the same as 10,000 neurons, because the layers is also equally distributed. And only the performance of one layer get worse, and we speculate it's because 1,000 neurons is no longer sufficient for one layer's model's piecewise approximation. So here is a data set side variation, and we have tests with m equals 5 and so on, and the result shows that 10, 20, and 50 fit best with a sample function and also with new points. The graph on the right is data sets versus the mean square error on new points.
So wait a second. So why is the MSE going up?
It's because of this oscillate.
Okay, good.
Okay. So with m equals 5, the sample point may not cover sufficient region to accurately represent the function. So this is why the mean square error on new points is higher. And with too many points, such as m more than 100, the interpolated function diverges due to Ron's phenomenon. And this occurs when sample points for polynomial interpolation are evenly spaced, and 100 samples in 512 points is high enough. So the model learned the incorrect representation, which is this part and this part, and that's why the mean square error got higher.
Good. Yeah, but you see that the interpolation becomes very jumpy there. Yeah, very good.
Yeah.
So you see that the network always does a smooth interpolation, right? So even if you cannot catch up with the real function, it still represents a smooth function, right? So it's nice.
Yes. So the neural network can approximate when the interpolated function does fits very represent the original function very well, and no wrong phenomenon occurs. And this allows them to learn a smooth and stable representation. So they have almost zero mean square error on sample point, also on the unseen point. But it can still approximate fairly well when the oscillation are not too severe, as the left plot. But it may fail completely when the oscillations become too extreme and the mean square error are very, very high. Okay. So this is a powerful task 1.
Is there a teammate for task 2?
Okay, I'm in charge of task 2, and here's my code. Please wait a minute.
We are 4 people, right? So let's see if everybody talks.
Okay, so here is the code I'm in charge. And here, the yellow line represents the polynomial generated with interpolation. Why do we choose polynomial? That's because the interpolation function does well when the function is a polynomial. So this can be a reference that our DNN is learning perfectly. Then how can we generate the polynomial? First, we get 10 random points per each function. Here is the generation. The generated y value ranges from -50 to +50. Then these 10 points between x range from 0 to 9. 10 points.
Okay.
Then the system will get the interpolation to extend the function set.
Yep.
Extend to 1,000 samples, range from 0 to 9.999. So after the whole generation process, you will get the yellow line, like here.
Mm-hmm.
Let's talk about the model. The model has 3 layers, 1 input, 1 output, and 1 hidden. The hidden layer consists of 2,000 neurons, a 2,000 times 2,000 matrix. And the activation, we use ReLU to speed up the calculation while decrease the chance of gradient vanishing. Here's the hyperparameters. The learning rate after testing, it's better to choose 10 to choose 0.001. And we also apply a weight decay temp to prevent overfitting. The number of epochs we choose is 400 to reach a better training performance. The loss function is NSE loss, while the optimizer is Atom, to ensure the convergence will be observed. Then the training data, number of training data, we give 20 batches and 100 functions per batch. Then after training, we will do the demo part. The demo part is to generate one random function, then print out the interpolation results with the DNN results, and we will do the comparison. The kernel shows that the prompt while running. So we can infer that the loss drops as we expected. The yellow line.
But look at the difference between train loss and test loss, right? It's gigantic, right? So your data set. Okay, go ahead. Go ahead. I'll tell you later. Go ahead.
So the data set of 2,000 functions can, with 400 epochs, can lead to this kind of training record. The yellow line doesn't search, so we can infer that the overfitting is small or never happens.
But what do you mean? Yeah, so it doesn't overfit, but it doesn't even fit, right?
But
so look at the difference between your training loss and your test loss, right? It's a factor of 1,000, right? So what happens there in your mind?
if you look at the loss, would be too high, but the loss is the sum of 1,000 points. But
Okay.
at least in this kind of scale, with the values between -50 to +50, an error of 1 or 2 in.
But your test is also in the same interval, right? Your test is in the same interval, or you also test outside the interval?
Sorry.
Your test point, right? The X value of your test points is also between 0 and 1, right?
Test points are on the yellow line, while the prediction is the green line. So some errors.
But it's still in the same interval, right? It's in the same interval, right?
Yeah, same interval. You can see here are some small noises that cause the loss. But
no, but I understand. But the loss is normalized, right? The loss is divided by the number of points, right?
No. Sorry, no. The loss is the sum of the square error.
No, but usually you average the number of points. Right? Can you go to the code? Let's see how you define the MSE. Go to the loss function when you train. Go to the loss.
Loss, right? But with all batches added.
Yeah, can you show me the definition of the loss function in the code?
Loss function here.
Loss, MSE loss. But inside the training loop, we'll go to the training loop.
The training loop is.
Yeah. There. Training batches. Go down. CPU, go down a little bit. Yeah, go down there. Epoch training loss. Epoch loss divided by number of batches.
But in my expression, the loss initially are billions, even trillions. So
really?
So 2,000 would be okay would be small for this case. Just because I said the range of.
No, but again, it's normalized by the number of points in the vector, right? The loss. When you call the MSE loss, is normalized by the number of points, right?
Yeah, but just because I didn't normalize the generated points, sampling points.
You didn't normalize. Come again. What do you mean by normalize?
You can see here the initial generating point is ranged from -50 to +50, which is extremely larger than other people did.
Yeah, I understand that. Yeah, because everybody normalized to between 0 and 1, right? That's why we gave you an example between 0 and 1.
Maybe in other people's cases, we can get only -0.5 to +0.5 because of NumPy's random function.
Okay, so let's go ahead. I have a suspicious. Yeah. I mean, Go ahead. It's not a problem. I just wonder. Yeah.
Okay.
Try to normalize, right, so that you are in line with the other people. Otherwise, it's.
帮我
I
开一下
want to
头
see.
衔。 I'm
Hmm?
talking to my members.
Oh, okay. Yeah, when you do the submission, try to normalize so that we see some. So you are in line with everybody else. Okay, go ahead. Task 2. Let's see
Okay.
this one.
Next page.
Next teammate, somebody else talking? Go ahead.
Okay, here is the other.
Do you have another student presenting? Because you have 4 people, right? I want to hear
We
all of
have
you.
another member in charge of this part. So let's
Go ahead.
So let's let him to do the presentation.
Good. Good.
是我吗？还是你？
你是瑞对不对？
没有，因为他们有第4个负责做统整的。
哦，好，那你的部分就你包吧，专场的。
现在画面是谁在分享？
现在画面是，
现在是我播 PPT， 因为他刚才群主说那个 Test 2的 PPT 可能要帮他播这样，因为他当初说 Code 跟 PPT 会切来切去。
所以现在是谁要？
就后来你先讲，后来我发现说我的部分用 Code 讲就可以了，所以现在就你直接拿那个。
哦，好。
然后如果有遇到我的图，你可以跳过那个。
还是我自己用我的简报？
对，你就用你的图吗？
那我用就可以。那个投影。Okay, so I'm in charge for the task 2.
Okay.
And what we face. Okay, so the first problem we encounter is we wonder how to generate the interpolated function fm. Do we use the random function, random generate points, or we use the sine function? And we think the sine function is too simple to this problem because it has a regular shape. So we use the random generated function. And the last person he mentioned he used the 10 random points to interpolate and 1,000 points as training data. But I think the 10 points doesn't really good enough to predict the function. So this is his outcome. So we have another DNN model that use 100 input and generate 512 output. But what we want to talk first is that the random point generate should be uniformly, because if we generate x and y sets all randomly, they might produce extreme values. Yes, this one.
Okay.
This is because the interpolated function we use might cause that, and we don't want to have the extreme value because they will be really hard to converge for the DNN function. And the last group have the like 10 times 10,000 100 million, like that scale. This is because this. that they didn't constrain the x value. So we have using random control points 2 to 10 to generate the barycentric interpolated function. And we have to constrain the control points x-axis, so we can have a more converged model. And in my job, I only do a comparison between the uniform and random sampling subset X. So I will only talk about the high-level outcome. My job is using this hyperparameter. So we use 100 to 128 and 128 to 256, and using 4-layer and the ReLU activation function. So after we training the model, we can compare by using this random this I don't know how to say this function, and this function can make some reasonable outcome, I think.
Okay.
So the left graph is for the uniform sampling subset X from the 512 points. We constrain the X to the specific X value, so they can have they can quickly converge and have a good outcome. And the right graph, we don't constrain the sampling subset X when we train the model. So the model only knows about the Y value. So I think the model cannot really predict the actual X value. You can see the bias between the actual function and the DNN prediction. And this function have a more explicit explanation, I think. So the lab uniform can really predict very well, and the random subset X cannot understand the function's x-axis, X coordination. Yes, and this is some outcome. Yes. Okay, so that's all about my part. I think that's all about our presentation.
Yeah, because the family you didn't do I would have liked to see a family of functions, right? So the family of functions that you generated, you sort of tailored it, right? So go back to the way you generate the random functions. Go back to this one here. Next slide.
This is for the prediction after we train the model. We want to see the
so how do you generate the data set of functions? How do you generate the data set of functions? Show me again.
This function is generated manually.
The data set of functions. Tell me again about the data set of functions.
Sorry, can you say that again?
The data set of functions that you use for training. Tell me again how it's generated.
Training.
So you do.
Oh, I didn't. Yes, I.
How do you generate the Ys?
Oh, I didn't post it here. And Y is generated randomly. We only constrain the X value.
The Y are totally random. No, you should do like 100, and then you do you do 10 points. Then you generate the barycentric interpolation, and then you sample from the barycentric interpolation, right?
Yes, we use random from 2 to 10 to generate points and select 512 points uniformly and use the interpolation to determine the Y value.
The barycentric interpolation, correct?
Yes.
Good. Because then when you do the test functions, these are functions that are Like, for example, a trigonometric function, right? The class of function, you will not learn it from the barycentric interpolation, right? Because it's periodic. But yeah, good.
I think we learned the barycentric interpolated method, so it cannot predict the periodic function.
Yeah, that's what I said. Yeah, that's what I said. Go back to the following slide. Yeah, go back. Go forward. Sorry, go forward. Go forward. Go forward. Go forward. Go forward. Go forward. Forward. No, forward, not back. Forward. Forward. Let me see the. Yeah, this one here. Okay. Next. And you say that the uniform does much better than the non-uniform, right?
Yes, because it's constrained the x value.
It's not that obvious, though, right? It's not that obvious. It's not that obvious.
You mean the right graph is good, or?
No, it's not obvious what you say. It's not obvious that if you choose x uniformly, right, then the interpolation would be better. I mean,
yeah,
it would be a little. You expect it to be a little bit better, right? Because there are no big interval in which you have no density of the points. But yeah. Okay, good. I like this part. Yeah, I like this part. Okay, good. Okay, so you were 4 people, right? Did everybody talk? No, there is somebody that didn't talk, right?
Yeah, because this time I respond for slides and do the writing report, and later I will edit the video report, and I allocate the process, the encounter, and summarize them on the slide. Yeah.
So I'll see you on the. I'll hear your voice more on the report, on the video report. Okay, very good. Group 4, go ahead, guys.
Hello.
Actually, guys, maybe, yeah. Okay, go ahead, guys, go ahead. I'm thinking next time maybe we split the presentation a little bit, and yeah. But go ahead, guys. Maybe next time we switch it up a little bit. Okay, go ahead, group 4.
So I'm waiting for the other guys to share its screen. Okay. Okay.
Go ahead,
so hello, we are group 4 and welcome to our presentation on using neural network to reconstruct function from sparse sample. And I'll briefly go with the problem definition. The core idea is to have that we have discrete samples of a function and we want to reconstruct a dense version of that function. And traditionally, barycentric interpolation could do this directly, but we are replacing our or augmented that with neural network to see how well they can learn this mapping. And okay, I'll direct go to task 1. So in task 1, we generated one barycentric interpolated function, and I use cosine, the function of cosine, and we then sample it at m point, where m could be 10, 20, 50, up to 200. And we fed this sampled point into a neural network, asking it to predict the full function. Okay, and we also test different depth, width, and activation function. Okay. Okay, next, 下一页. Okay, I'm going to introduce the result. These are the results of different different size of data set, and we have 4 kinds of data set. That's for 5 kind of data set, and the other one is at the next page. Okay. Okay, this is the other one. 下一页.
Interesting, yeah.
Okay. Okay. Now I'm going to discuss on the effect of dataset on MSE. And in the experiment, okay, this plot is the x-axis of this plot is the data size in million, and the y-axis is MSE in log scale. And
yeah, it's good. It's explode, right?
yeah, so we use the hidden layer. The hidden layer we use is 128, and
Okay.
for two layers, and the activation function we use is the ReLU function. So there's three metrics: the training point, and all points is how the training point is how well the model fits the training data, and all points generalizing over the entire function domain, and unseen point generalization on truly unseen data. So the MSE initially improves with more data than worsens. So for small data set, 10, 20, 50 points, MSE on all point and unseen point decreases as data set increases. So the data set when goes to 10 to 20 to 50 shows a steady improvement in generalization. But beyond 50 points, performance degrades rapidly. At 100 points, MSE on unseen points jumps to 44.53, indicating a poor generalization. And at 200 points, MSE on unseen points skyrocketed to 7,000, so complete failure in function approximation. And about the convergence behavior, about the early stopping and convergence behavior. For small data sets, the model trains quickly and stops early due to convergence. It's not shown here, but one can, according to the result, for 15 points, it stopped earlier at 2,000 epochs in 3 seconds.
Okay.
And for 20 points, it's early stopping at 6,000 epochs in 8 seconds. And for 10 points, it's stopping at 4,000 epoch and 11 seconds. But for larger data set, the model trains for longer but does not converge as well. For 100 points, it's trained for 9,000 epochs for 14 seconds, but error remains high. And for the 200 points, the train for 9,000 epochs in 18 seconds. And still, the MS still worsened drastically. So I think this suggests there's overfitting at small data size and poor generalization at larger size. So
but that's because interpolation becomes so unstable, right? So you understand it now. Yeah. That's what happens. Go ahead.
So
very good.
Yeah, so there's the potential reasons. So for larger data sets, there's maybe over parameterization and poor learning dynamics and
no, but it really depends on the interpolation. The interpolation become very unstable. It's not the network, right? It's the interpolation, I think.
Yeah.
It's not the network.
Yeah, so the optimal data size in our experiment is 50 points so far, and is aligned with the double descent phenomenon observed in deep learning. Initially decreases error with more data and followed by increase due to model overconfidence. Yeah. So, Xiaoyu. Okay, the next part we explores the structure of the architecture, and we did 5 experiments. Xiaoyu. And there's another one, Xiaoyu. Okay, I'll just directly jump to the result. And so we have 3 kinds of structure. The first one is one hidden layer with 100 neurons, and the next is 2 hidden layers, 100 neurons each, and 3 hidden layers, 100 neurons each,
okay.
and 500 500 neurons in one layer and 2 hidden layer. The next one is 2 hidden layer with 250 neurons each. And the last one is 5 hidden layers with 100 neurons each.
Got it.
So in this experiment, we use data size of 100, and the activation function is ReLU. So for single layer neural network, the 100 neural one, the first one, I think it's achieves best generalization. The MSE on unseen point is only 0.0022.
Okay.
And although it has the smallest number of parameter, but it performs almost the best. And the 2-layer network, the second one, the 100, 2 times 100, is the worst. The MSE on unseen points explode. And it suggests numerical instability in training and might be due to exploding gradient. And the intermediate depth provides good trade-off, like the 3-layer networks. It performs also well. And we found that if the neurons, the number of neurons increases, the wider but shallow network, like 500 neurons, also works well. And the deep network suffer from overfitting and instability. So for the 5-layer model and the 2 times 250 model, they both generalize not very well. So I think in this mission, 1 layer is enough for generalizing this interpolation job. Okay. And the next experiment, we explores the different activation function. We choose 8 activation function. These are 4 of them. These are another 4.
But which ones are they? like the top left. What's the activation on the top left?
Left.
Yeah, which activation function is it?
Top left.
It's not written, right?
I will show it.
Tell us which function gives you which loss, right? Otherwise, how do we know?
I will show you.
Go ahead.
Okay, these are the 8 functions. So the top left function you mentioned is the EL.
Leaky ReLU, yeah. Okay, good.
Yeah. So okay. So based on this graph, okay, you can find that I mean we use the one data set of 100 and the 128 for
the
2 layers, the network model. And so the best activation function for generalization, I think, is leaky ReLU and ELU, the exponential linear unit. They both.
So also the other groups said that they had very good results with the leaky ReLU, right? Because they don't have so many dead neurons. Yeah. Go ahead.
So for the leaky ReLU, it converts only 2,500 epochs. It's the fastest training, and the exponential linear unit stopping at 3,200 epochs, and it's also the second fast training. And it also the ELU perform also better than the ReLU, the ReLU, the classical ReLU. the standard value. So confirming that exponential scaling stabilize the learning. And the result of leaky value suggests that adding a small slope in negative regions prevent dying neurons. And the sigmoid also performs well. So I think that for small data set, sigmoid works, but is inefficient because it takes longer to converge. It's converged at 9,000 epochs. And other moderate performers are ReLU, rectified linear unit, and I think it performs worse because it's possibly due to some dying neurons. And the Jello Gaussian error linear unit, it's better than Soft Plus, but not as good as LU or leaky ILU. And others are catastrophic failures like tangent, hypertangent. Its training MSE is very low, but generalization is terrible. So it's not suitable for this deep network job. And the hypertangent saturate, leading to severe gradient issue. And when it comes to Soft Plus, it's slow convergence, poor generalization, and maybe struggle due to slow activation growth. And scaled exponential linear unit is exploding loss values from the start. So as it is known, this scaled exponential linear unit is known to work best with self-normalizing network, but without careful weight initialization, it fails catastrophically. So, 下一页 ，next page，
下一页 ，OK，
上页，不好意思，上页，我这边反应慢的，上页，
这样，
为什么没有跳出来？
没有，他们连续的。
你在 hypothesis 那页吗？你跳到 hypothesis 那页，就你的前页，OK， 好，OK， 好，OK， I'll go with.
Okay, good.
So there are 3 hypotheses we originally made, but two of them are refuted and one is supported. And the first one is that we originally thought that the larger datasets always improve the generalization, but which is not true because the dataset size plot shows that after a certain point, MSE increases. So likely due to difficulties in interpolation beyond available training data. And the second hypothesis is that deeper network always generalize better, but it is also refuted. The network depth plot shows a huge instability for Q times 100, suggesting that different networks are prone to exploding or vanishing gradient, and that ILU-based activation functions are the most stable. So according to the previous graph, that the activation function shows that the ILU and leaky ILU, the ReLU and leaky ReLU outperforms others. Yeah, so that's the conclusion for the task 1, and the other person will introduce the task 2.
Okay, very good, guys.
Hi everyone, I'm gonna introduce our challenge 1, text 2 of challenge 1. And first, I'm gonna quick introduce the primary task. Our main task is that we consider a family of barycentric interpolated function. Each function is discretized into 512 points in 0 to 1. And then we select 100 of these points as input and train a deeper neural network to predict the entire 512 dimensional function curve. And our key steps is first, randomly generate multiple functions to form a data set. And then the neural network takes a 100-dimensional subset as input and output 512 dimensions using MSE loss for training. And third, we evaluate how final performance is affected by data set size, network and architectures, and activation functions. Yes. So next part is results and observation. So first we set data set size M to from 10 to 20, 50, and 100 and 200, and observe how it affects to the test MSE. And the results, the value is already on the figure. And for M equal to 100 and M equal to 200, we encounter non-loss during training. So the final test MSE still reports roughly 0.0107, which is larger. I think we think the possible reasons is because we applied normalization to some functions. Dividing by 0 might occur when interpolation output are close to 0, leading to runtime warning and non-loss. Yes, and our observation is that bigger data sets are not always strictly better. So let's continue. Next part. The figure on the left side, we test various architectures, like 1 times 100, 2 times 100, and others. We can see that the test MSE generally falls in the 8.4 to the power of minus 3, 10 to the minus power, 10 to the power of minus 3, to 9 times 10 to the power of minus 3 range. For instance, you can see that this one, 2 times 100 and 5 times 100 performed relatively well, getting as low as around 8.3 times 10 to the power of minus 3. We find that single layer networks like this one, 1 times 100 and 1 times 500, or this one, 3 times 100 may do slightly worse. Okay, and then next is the scatter plot maps the number of network parameters against the test MSE. We found that the monotonic relationship in this figure. So as shown in the figure, some models with fewer parameters actually achieve lower test MSE than certain models with more parameters. So we think this indicates there's no straightforward trend of more parameters leading to the lower error. And next is the activation function test. Yes, like ReLU and hyperbolic tangent, sigmoid, and others yes. So the value is already key on the figure. And we can find that the hyperbolic tangent performs as the test, and ReLU variants were fairly stable, and sigmoid and SeLU were in the middle or slightly worse. However, these outcomes can also depend on initialization and learning rate, and do not imply sigmoid or SeLU are inherently inferior. Yes, and next is plan work and next step. We plan to enhance training stability and adopt advanced strategy. And we will also test alternative loss function, like L1 for handling outliers, explore splines or polynomial expansions. Yes, to assess performance under noisy condition. And here's our contribution.
Very good, guys. Very good.
And
Yes, we're going a little bit longer, so let's do group 5 a little bit quickly, and then we hear from Solveig, and then.
Thank you for your listening.
Thank you. Yeah. Group 5, come. Group 4 did very well. I don't want to rush you guys.
Wait for me.
Group 5, Group 4 did very well. It's just that, you're going very long today.
Could you see the screen?
Yeah, go ahead.
Okay. So, hi everyone. Hello, Dr. Stefano. I'm Li Junshun from Group 5. And we are going to introduce about the challenge 1. And first, we need to build a DMN model to train or to reconstruct a function by using an interpolate method, which is called barycentric interpolate function. And so what does this function comes from? Is from different kind of interpolation can make a generative function, and here we use barycentric interpolation. And besides, we also test many different kind of selection methods to build to build some nodes, because you notice that in boundary, many function will become those generative function will become unstable. So we need to solve this problem in test 2. And in test 1, we didn't face this problem, but we just discussed about the variable and change variable, and to discuss about the changes in the chain model. So
let me stop you here. I think you're sharing your PowerPoint, but you have to share the window with the PowerPoint presentation. Try to switch the presentation, because we don't see you changing slide.
Oh, you didn't see a slide, right?
Just change the window that you're presenting. No worries.
So is that okay right now?
Yeah.
Okay. Okay, so we have an answer to the DMN model to learn now by using the barycentric interpolated function. And in test 1, we need to change some variable to improve the training. And in test 2, we had to build a multi-input model so that we can put a function and directly have the answer and know its MSE and other information. And in test 2, it's special because we didn't need to test the model or train the model one by one every time we have a random function, but we can have just once training. So it's pretty convenient, but it's because the multi-input model and let us can do this thing. So okay, we go straight to test 1. Okay, so we can talk about the coding detail first. This part I use barycentric interpolation to build a function as a ground truth. You can think that it's a right answer, and when you're learning, you can think a DNN model is a student, and this one is the book you need to read, and the right answer is called a barycentric interpolation, though it's not a real function which we have defined here. Okay, so ground truth is means the right answer. So next part. Okay, so next part is activation function and other parameters here. And we defined the model and the structure of the model here, and we can change some parameter like the width or the width or the depth of the hidden layer, and also the activation function. And this part is about the narrower training, and you can notice that this part we have optimizer, and optimizer is about the learning rate, and we know that if learning rate too high or too low will both have a negative impact, right? So we need to choose a appropriate learning rate or an optimizer, which we can better to update the learning rate. If the learning rate is too low and it's trained very long, and if the learning rate is too big, and it may be overfitting. So that's why we don't want to see that phenomenon happen. So yeah, so this part is pretty important to say an appropriate optimizer. Okay, and this part we evaluate the model and we calculate MSE here, and also previous part we introduced the time function because we need to define the starting time and counting the time and counting the training time, and we need to compare with other variable. Okay, so we finished calculated MSE here, and also finished plotting in next part. Yeah, so the fitting function is finished in this part. Okay, so next part is for another group member.
Okay, can you hear me?
Loud and clear.
Okay, so here is the variation part. And our first comparison involves different activation functions. For instance, the sigmoid function outputs values in the range of 0 and 1, which makes it thus ideal for regression tasks, where outputs may be large or negative. And it's because the sigmoid function has tendency to saturate. When inputs are very high or very low, its derivative becomes extremely small. These saturates cause the gradient to vanish during backpropagation. So it's slowing down the learning significantly and make it the performance poor. 下一页. And in contrast, the hyperbolic tangent function outputs value in -1 and 1 and is zero-centered. And this provides more balanced gradient updates across layers, making hyperbolic tangent a more suitable choice for our regression problem. And you can see the arrow here is lower than sigmoid. 下一页. And the experiment result shows that with the sigmoid function, the gradient converges more slowly, resulting in a training time of approximately 0.9 seconds, whereas using hyperbolic tangent reduced the training time to about 0.78 seconds. 下一页。We also explore the impact of hidden layer width. Increasing the number of neurons generally improves accuracy, as a wider layer can capture more complex functions. Here we use a rectifier activation function to illustrate the difference in fitting performance. 下一页。The result indicates that a network with 100 neurons per layer shows a larger mean square error, and compared to one with 256 neurons. However, the wider network requires a longer training time, and this is the trade-off of machine learning. 下一页。And here we test the width larger than thousands. When the width is increased to more than 1,000 neurons per layer, performance deteriorates. This is due to optimization difficulties from a large number of parameters, which slows down convergence. Our experience suggests that optimal neuron count lies between 256 to 512 neurons per layer.
Very good.
And further comparison between 1,000 and 2,000 neurons shows that overly wide networks not only extend training times, but also lead to degraded performance, emphasizing the need to find a sweet spot in network design. 下一页。And then is the variation via different depth of hidden layers. We investigate the impact of network depth, and we use 4 and 8 layers here. Theoretically, deeper networks can approximate complex functions more efficiently. In our experience, increasing the depth from 4 to 8 layers significantly reduces the error. 下一页。And here's the comparison. The 8-layer model demonstrates superior accuracy compared to the 4-layer network. Although increased depth also extends training time, the gain in precision makes it worthwhile. 下一页。And here is the deeper model we test. However, when the network depth increases to 11 layers, performance worsens due to training difficulties like vanishing or exploding gradients. To mitigate this, we integrated a ReLU activation function. 下一页。We then test 11 layers and 16 layers. A comparison between them reveals that excessive depth does not yield the expected benefits and can even harm performance because of training challenges. I think we need more data samples, or we need a larger training time to overcome the deeper model. 下一页。The size of sample data set also affects the model. We test 25 sample points and 100 sample points, and we see that when only 25 sample points used, the network struggle to capture the function's behavior fully. And when we use 100 sample points, it introduced too much detail and making the function unstable for the model to feed. 下一页。And our experiments indicate that 50 sample points provide a good compromise, sufficient information without making the function overly complex. And here you can see the result. With less or too much sample points, our prediction will be not accurate. 下一页。Next, we tackle a more advanced task, interpolating a class of barycentric interpolated functions. We built a multi-input DNN model that takes a 100 length vector as input and produces a 512 length output, enabling simultaneously fitting of multi-functions. 下一页。So why do we use Chebyshev nodes? Uniformly distributed sample points often cause dramatically oscillations at the boundaries, a phenomenon known as Runge phenomenon, leading to large interpolation errors. And Chebyshev nodes mitigate this issue by clustering more points near the edge, thereby stabilizing the interpolation. And furthermore, if the number of interpolation nodes is set too high, such as m equals to 75 or even to 100, the function becomes overly sensitive to minor fluctuations in the data. This overfitting at the boundaries can lead to signal distortion, as the interpolated curve oscillates excessively instead of capturing the smooth underlying trend.
Thank you for telling me this. Yeah, I didn't know about these Chebyshev nodes. Go ahead. Go ahead. It was very good. Very good.
Okay. This slide shows how we generate random functions within 0 and 1 interval by selecting random frequency and amplitude. This ensures that every generated function is unique, providing diverse training samples. Here, another example of the random function generation process is displayed, highlighting the variety and complexity of the function, which is crucial for testing the robustness of our model. So we designed a multi-input DNA. We design a multi-input DNA model to improve training efficiency. This model allows us to feed up to 1,000 random functions in one training session, significantly reduce overall training time. So this slide presents the fitting result for 6 selected functions out of 1,000 generated. The close match between the model's output and the ground truth confirms the high accuracy of our approach. Overall, both the training and test accuracy are high. The fit function closely resembles the ground truth defined by the barycentric interpolated functions, demonstrating the effectiveness of our methods and the stability provided by using Chebyshev nodes. Okay, so here's our presentation, and we provided a clear understanding of our approach and using deep neural network for function reconstruction and interpolation. Thank you.
Yeah, so the only thing is these random functions. Like you saw the previous groups that like they had more challenging functions, right? Because here you have a trigonometric function, it's a little bit too simple. Try to change the part so that you do like the other groups, right? So you generate an XY pair, then you generate a barycentric interpolation, and then you use that as a random function, as a function to learn. Otherwise, you know, like you saw the other groups, right? If you just take a trigonometric function, everything it's easy. It's not very interesting. Okay.
Yeah, thank you.
Okay.
Yeah, it's just a small change. Okay, guys, let's take another break. Next time, please, guys, try to stay in the 20 minutes, right? So I'm happy to listen to you. There is no problem there, right? It's just that now we took, it was almost like 30 minutes per group. So I need you to be more on time with the 20 minutes, okay? Because otherwise everybody gets tired, and then the last groups, they don't get so much attention. So let's do this. We take another 8 minutes break. We come back at 50. Then Huawei will tell us the presentation will tell us something about interpolation, and then we stop there. Okay. See you back at 50, guys. Okay. Huawei, get ready. Generated is also good. Network architectures. Okay, very good, guys. Torway, whenever you want to go ahead.
Okay.
Yeah, the guys, again, so I like to listen to you, but yeah, let's try to stay in the 20 minutes, okay? I think today we went super long.
So
Go ahead, sorry.
I want to recap on another method of interpolating data points by using Fourier transform. And here's a simple explanation on understanding Fourier transform. I won't go into too much of the mathematical detail, but this is a more pragmatic approach on explaining the mechanisms. So, introduction. What is Fourier transform? Fourier transform converts signals between time domain and the frequency domain. Well, but the experts on Google or YouTube videos often describe them as a mathematical tool, but the math can sometimes be too complex and overwhelming. So in my presentation, I aim to simplify the concept. And here is the outline. I will make 3 examples on the applications and explain on the differences between time domain and frequency domain, and dive a little more into the frequency domain part and how sound is stored digitally. Okay, so what can Fourier transform do? It can help with analyzing signals, so to speak. Like applications include, first, space signals and astronomical data analysis. Imagine we're collecting radio waves from space, and these signals, of course, contains waves from different corners of the universe, so they look very chaotic. However, after applying Fourier transform, we can break down these chaotic signals into individual frequency components. By reconstructing them, we can understand what kind of signals are present in the original data. Second, music processing. If we want to make a karaoke track without the singer's voice, we can use the Fourier transform. If we analyze a song using the Fourier transform, we can decompose it into a collection of different frequencies. So we can create the tracks by filtering out the singer's voice and keep only the instrumental music. And this is how karaoke tracks are created. And lastly, data compression. Fourier transform can also help compress data. When we transform a signal from time domain to the frequency domain, we can choose to use fewer frequencies to reconstruct the signal. This allows us to reduce the file size while keeping the waveform almost the same. In MP3 compression, it reduces the audio file size, and JPEG compression, it reduces the image file size. So, time domain versus frequency domain. Well, in the time domain, which is the world we live in, we understand the world by observing different locations, different times, and that's what our brains tell us. our brain builds an understanding of the world by recognizing objects at specific points in time and space. Even sound, while we can't see, follows the same principle. At any given moment, a sound exists as a form of vibration of energy at a specific location, such as our eardrums. That's why we can hear things. And in the frequency domain, it's like viewing things in a more hyperdimension. Like if we view things from the frequency perspective, it's like the universe unfolds into a multidimensional static dataset. And from this dataset, we can reconstruct what the world should look like at any given point in time and space. And how do we describe things in frequency domain is using waves. And waves are composed of two things, frequencies and amplitudes. Now, waves in the frequency domain. A single frequency wave can be represented using trigonometric functions like sine waves and cosine waves. But regardless of whether we use sine or cosine, they both represent a type of rotation. So in 3 dimensions, we can use our imagination on this one. These waves look like a spring moving forward in a helical shape. If we view it from above, we can get a cosine wave. If we view it from the side, we get a sine wave. Now, different frequencies will result in a different waveform. And the most important part is that different frequencies create different pitches of sound. The higher the frequency, the higher the sound. And next, we move on to the amplitude and the sound volume. Now, this is pretty intuitive. Larger amplitude corresponds to louder sound, and smaller amplitude, quieter sound. So waves are essentially like keys on a piano, like do, re, mi, fa, sol, each producing a specific frequency. And the more complex waveforms in our daily lives are formed by combining waves of different frequencies and amplitudes. Now, how do we store sound in a file? When we use microphone to capture sound waves, we sample the waveform at fixed time intervals. Now, x-axis, we can represent time with that, and y-axis represents amplitude. And at each time step, we record the amplitude value, storing it as a set of xy points. Okay, and by saving all these sampled points, we can get a wave file. But a smarter way to store digital sound is to only store the frequency, volume, and the duration of each music note in the MIDI format. MIDI format are much efficient, and MIDI files are much smaller than wave files. And in the 80s and 90s, early computer games used MIDI files to store music this way. And a single MIDI file is just a few kilobytes in size, but if converted to a wave file, the size can increase up to 1,000 times. Now, converting recorded sound into frequencies. Now, the real world is noisy. The recordings may contain various sounds other than the musical instruments. It may have some noises due to a lot of reasons, but we don't want that. Now, we can use Fourier transform to decompose raw sound data into its component frequencies. So it answers the questions, which frequencies make up the sound? Okay, so for a transform in action, we can recreate a waveform using only cosine waves of different frequencies. each wave is scaled using a coefficient, let's call it A here, to determine its amplitude. Now, scaling factors affect the size and direction of the wave. And more frequency components can lead to a closer reconstruction of the original waveform. Now, we can visualize the frequency domain by plotting the scaling factors as a bar chart. Like, we can see that each frequency component respective effects on the total signal. Transition from a continuous waveform to a discrete frequency representation is what we did here. And each bar represents how much each frequency contributes to the original waveform, so to speak. So I will use an analogy here to give you an intuition how Fourier transform work. It's, say we're analyzing a person's appearance and personality. A person's traits can come from multiple influences, like their mother, their fathers, and their significant others. Sound wave is made up of multiple frequency components, like in this manner. Fourier transform determines the scaling factors of each frequency. And using this mechanism, we can even interpolate what future data should look like. So how do we find wave components? The algorithm uses dot products to project, project one vector onto another. It converts a wave into a vector by slicing it into smaller segments and sampling the y point as the picture here. And we arrange these sample points into a sequence to represent the wave in time-space domain. Now we can use the dot product for a transform. For example, to get a sub 1, we take the dot product of the original wave vector and the unit wave vector of the frequency, which is just cosine 1 pi t, and multiplying the corresponding values at each sample point, we can sum them up to get the projection length here. Yeah. And we divide the result by the total number we sampled to get the average values. It's like we treat the functions like a vector here, so to speak.
Correct. Yeah, so like in a vector space, you have an inner product that you understand from the Euclidean geometry. And also in the space of function, you have the same concepts, right? You have an independent function, you have inner product, you have power. So it's...
Yeah, of course. And Euclidean space analogy here. Okay, so here's the summary. We observe the original wave in time-space domain, sample its values at small time intervals, and store them as a vector. And we can convert frequency unit waves into time-space unit vectors. Then we use the dot product to find out how much each frequency is affecting the original wave. And we can reconstruct the original wave by multiplying each unit by its respective component length and summing them up. Now, here is a demo by this website. Now, here are the original waveform. And after the Fourier transform, we can get the closed waveform, but something's missing. We still have two more things to consider, which is what we missed is the negative frequency. Now each frequency has a spiral moving in one direction, like I mentioned earlier, but we have to consider another direction, which is moving in the opposite direction. And these are called negative frequency waves. A negative frequency wave is like an mirror image of the positive frequency, but it travels backwards in time, which is counterintuitive, not very easy to think of. But here, if we look at the Fourier transform table, like for example, in the cosine part, see, we just don't get just the positive frequency. You also get the negative frequency. So we need to consider both positive and negative frequency. Like here, if we use negative frequency now, we get a closer approximation. But there is still one thing we miss, which is the zero frequency component. The zero frequency of sine and cosine waves are also important. We can't reconstruct the original waveform without it. Now, sine of 0 is just a flat line 0. Now, cosine of 0 is a flat line 1. And multiplying the cosine 0 wave by a scaling factor shifts the entire waveform up or down. And this scaling factor represents the overall center position of the original waveform. Here we can use the zero frequency, and here we get the original waveform. And we can test out the resolution. Like if we just used 10 data points, we don't get a close approximation. But if I use more, we can get a much more accurate result. So, how frequency components affect compression? Lower frequency components determine the overall shape. Now, while higher frequency ones add to the fine details, and removing the higher frequency details reduces the file size, but it also loses quality. And this explains why compressing sound or images can cause distortion. Now, visualizing Fourier transform with spiral waves. Instead of breaking a frequency wave into separate sine or cosine waves, we can use their scaling factors of parameters to determine the radius of the spiral motion and starting phase, draw the circular motion of each frequency, and stack them all up. And here, I know this context is not very easy to understand, but this is what I mean. Like we have all these sine and cosine waves, but we can represent them using circles, right? And we can just stack them up together and get this visualization. And we can also just draw any shape, and we can use the Fourier transform to reconstruct the waveform.
Yeah, this is the 2D case, right? So this is the 2D Fourier transform.
Yeah, this is just the 2D case. Huh? Yeah, see, any shape works. Okay. So that wraps it up. Yeah.
Okay, thank you, Joey. So guys, because I asked, and some of you haven't done the Fourier transform yet, and you guys will see the Fourier transform a lot in the next year. So you're going to see it in like 3-4 courses. But thank you, Zoe, for giving you this introduction. The idea is that, so there is a lot of engineering theory which is built on Fourier transform, and you guys will have time to study it in more detail. But it's nice for you guys to have an introduction now. Okay, guys, so Gaida, please release the new groups as soon as you can. Friday, we release the new challenge. Zoe will give you the link to submit the inter-report and the intra-team evaluation form. And then, the new challenge starts on Friday. Fix the things that we discussed today in terms of the final project. And then, so please, next time, try to stay on the 20 minutes mark, because today we went super long. So I wanted to cover the optimizers, but I'm not going to be able to cover the optimizer by myself. So please just cover this by yourself, okay? So, so this lecture 10, it's very easy, right? So, cover this lecture, right? The one about optimizers, So just do these 2 slides. You just do them by yourselves, since today we went so long. And otherwise I'm going to be here for another 10 minutes if you have any questions. Otherwise, I think we're all fairly tired today. And let me know if you have any questions or any comments either here and now or Slack later. Okay, guys, I'm gonna stop the recording. Ciao, ciao.
Ciao.
Ciao, ciao.